So this is going to be a video explanation for problem 3 on the asymptotics review worksheet. So let's start off by just understanding what the problem is asking. Okay, so what we do is we set the hash code and equals methods of the ArrayList class as follows below. Okay, so this equals method should be pretty similar to what we've seen in lecture or what we've even implemented in the project. All that we're doing is we make sure that the new object that's passed in is of the same size. It's actually an array list, etc. Otherwise, we return false. Then in this for loop, we do a pairwise comparison of all of the elements between the array list that's passed in and ourselves. If any of them are different, we return false. Otherwise, we return true. Okay? And then let's just note that this is going to take theta of n time in the worst case. Right? If we have to iterate all the way to the end. Okay? Or this whole function, that is. So looking at the hash code of an array list, which is a bad hash code for this problem, is going to be the sum of all the elements in the array list. Okay? And this is really easy to implement. In practice, we could just have a sum variable that's cached similar to the size. Okay? So looking at this problem, it's a little confusing. What we're doing is we have this hash contents function. It's going to keep calling itself recursively, right? Each time, what we're going to do is, let's say that we have a list defined as 1, 2, 3, 4. Each time what we're going to do is we're going to remove the last person from this list, okay? We're going to set, which the set operation, what it does is it changes the element at index 0 to be the new value that's passed in here, okay? So what we're going to do is set the value at index 0 to be the result of this recursive call to f, or not recursive call, this function call to f, okay? So let's just say that somehow this changes to 10. We have no idea what f does, but we know it runs in constant time, and it's going to spit out a number, okay? The next thing that we're going to do is we're going to add this list to our hash set, right? So recall how a hash set works is we have an underlying array, okay? So this is going to be my hash set, right? And it's partitioned into these buckets. So what we're going to do when we execute set.add_list is we compute the hash code of the list. We go to that bucket. Let's just say it's bucket, I don't know, 0, 1, 2, 3, 4, 5. In this case, the hash code would be 15. 15 mod 5 is 0. So we would actually go to bucket 0, and then we would put the list here, right? So we put the list at bucket 0, okay? And then we're going to repeat this process until the list size becomes 1, okay? So let's just do one more iteration of this. Actually, yeah, let's do one more iteration, and let's kind of see what's going to happen. So after doing one more iteration, what's going to happen is that we will remove 3. We will somehow change this element. Let's just change it to, I don't know, 15, sure, right? We're going to take the sum, which is 17, right? So our new hash code is 17, which corresponds to 17 mod 5, bucket 2, right? We go to bucket 2, and then we're just going to put that list in there, okay? And we're going to keep repeating this process until the list becomes of length 1. So what we can see when we're trying to figure out the worst and best case, let's try to break it down into what can possibly happen when we repeat this process, okay? There's kind of two possibilities of what can happen. Every time I take my list and I put it in the hash set, I can either put it at a bucket where there's already something there, or I could put it at a bucket where there's nothing there, right? Do you guys see that? There's two cases. I put list in new bucket, or I put my list in an old bucket, which means there's already some list put there in the past, okay? So let's kind of walk through each case and see which takes longer. Intuitively, I think that makes sense. So in the case that we put the list in a new bucket, let's consider case 1. What's going to happen in terms of the code is we compute the hash code, right? We go to this bucket, let's say bucket 4. We say there's nobody here and we're done, right? So the insertion process was really, really fast. What we can say for case 1 is that it really took constant time, right? Because all we're really doing in this case, let me recap. This is very important to understand. All that we're doing is we compute the hash code. How long does computing the hash code take? Well, sum is a cached attribute of the class, so it takes constant amount of time. Then we go to the bucket 4. How long does it take for us to go to bucket 4? Constant time. We check there's nobody there in constant time. So we can see that case 1 is going to take us constant time. Let's consider case 2 then. So for case 2, we put the list in a bucket where we put the list in the past. Okay? So in this case, let's say that on the third iteration, I happen to put the list at bucket 2 again. Okay? What's going to happen now is we're going to ask ourselves, is this list equal to the new list that's passed in? Okay? We're going to say, is the existing list at this bucket equal to the list passed in, right? Because that's what we do when we use a hash set. We check, is the key I'm inserting, right? This is in your guys' hash map lab. Is the key I'm inserting equal to somebody at that bucket? In which case, there's no work we need to do. We'll update the value. The same logic applies in hash sets. We check, is whatever is there equal to what we're inserting? In which case, we just like stop, okay? So this is the crux of the problem, and it's very confusing for a lot of students, is that when we're inserting a new list, let's say this is what we're inserting. This is what we're inserting. Everybody in this hash set, they're all pointing to the same list because that's how we store array lists in Java, right? So what that means is that when we change the array list, right, everybody in this entire hash set is all pointing to the same array list, right? So they're all equal. You all see that? This is kind of cool. So everybody in the hash set is equal, which means that the existing list at this bucket is indeed equal to the list that's passed in, right? Because they're all the same reference. So let's see, how long will the equals method take if two things are equal, okay? If we look at the equals method, we'll realize that if the list that's passed in is equal to our list, what will happen is that this will never happen, right? We will never short circuit, and we will always take theta of n time when two equal lists are given, okay? So we're kind of like going on a good track here. What we've realized is that in the two cases, in case 2, it's going to take us theta of n time, right? Or proportional to the length of the array list at that current moment in time. So let's think about it. This is probably going to somehow lead to our best case behavior, right? This is somehow going to lead to our worst case behavior. So in the best case, what if every time we reinsert the hash set, it always goes to a new bucket? That's totally possible, okay? So my idea, let's get rid of some of these drawings to make it a bit clearer, is that every time we reinsert the list, it always goes to a new bucket, right? So let's say the third time it goes to this bucket, the fourth time it goes to this bucket, right? It's always going to a new bucket. So what's the total amount of work that we're doing here, right? What's the total amount of work? Well, the total amount of work is going to be a constant amount of work each time hash contents is called, right? So if we do a constant amount of work each time hash contents is called, right? And we call hash contents n times, because that's the length of the list, what we can see in the best case, it's going to take us theta of n time. right? And this, again, to reiterate, is the possibility when every time we reinsert the array list in the hash set, it keeps going to a new bucket, okay? Does anyone have any questions there before I talk about the worst case? Okay. So the worst case is the possibility when every time we insert a hash set, it always goes to the same bucket, right? Let's kind of like walk through an example to see when that would possibly happen. So let's start from scratch, okay? Let's say that this is the contents of our array list, right? 1, 2, 3, 4, same as beginning. What's going to happen the first time is we remove this element. Let's just say we remove somebody at the end. Then what we're going to do is we're going to insert this array list into our hash map or hash set, right? So we see that this is hash code 10, right? I think I can do the math. Yes, it's hash code 10. So we go to, I realized I've been miscomputing the bucket the entire time because the length of this is actually 6, not 5, which is a little embarrassing, but it doesn't really matter for the sake of this problem. Okay, so I definitely thought the length of the hash map was 5. Let's just make it 5. 5 is a way better number. Okay, so yes, the length of the array was actually 5 the whole time. But anyways, so we take the hash code 10, and then we say, what is 10 mod 5? That gives us 0, so we go to bucket 0 and we insert the list, like so, okay? So what's going to happen the second time around is we remove the number 4, right? We remove the number 4, and then the sum is going to decrease by 4, right? It's going to decrease by 4. So let's say it's now 6. So in order for us to insert the array list and make it go to the same bucket, what if when we call f, this value becomes 4 plus 1? What if this becomes 5? Right? What if every time we remove somebody from the end, in order to ensure that the array list goes to the same bucket, we take the value we removed and add that to the beginning? Okay? Now what's going to happen is that the sum stays at 10. And then when we insert the hash map, or the array list the second time around, we go to bucket 0 again. Right? Do you guys see that? Okay, now let's do one more iteration of this process. We're going to remove 3. We're going to take 3 and add that to 5. It becomes 8. Right? The sum stays the same. The third time we insert, it keeps going to bucket 0. It realizes it's equal, and it doesn't reinsert there. Right? So in this case, the total amount of work that we're doing, the first time it's going to be, let's say work. The first time it's going to be like around n work, right? Because that's the current length of the array list. So what we can say is that as the array list gets one element smaller each time, our work goes down by 1 each time. And then we see we have the sum of n plus n minus 1 plus n minus 2 plus 1, right? So in the worst case, it's n squared. And that's the possibility that every time we reinsert the array list, it keeps going to the same bucket, in which case we realize it's equal, but in order to realize it's equal, it takes us n time. So then we perform n time the first time, n plus 1 time, n minus 1 time the second time, and so on. Okay, so does anyone have any questions? Any questions? Feel free to like speak out loud or okay. Any questions? Okay. Wow. Interesting. Okay, so we'll quickly finish it off here. So now we're going to define f to ensure the worst case runtime and define f to ensure the best case runtime. Okay. So we've kind of touched upon this from the previous part, but in the worst case behavior, we want f to make sure the sum stays the same the entire time, right? So in the worst case behavior, we want the sum to stay the same the entire time, right? Does that make sense? So what we want to have happen is that every time we have some array, right, like 1, 2, 3, 4, 5, if we remove 5, we want this value to be what was there before plus 5, right? So the sum stays the same. So we can see here we can do return first plus last. Does that make sense? I kind of touched upon this a lot, like in the previous example. It's just implementing in code more rigorously. Okay, so let's move on to the best case. And I'm going to ask you guys a question. Will this ensure the best case behavior if I just return first? Yes, no? Okay, I want to make this semi-interactive. So somebody can take a side. Yes, it's going to ensure the best case behavior. No, it's not. Ooh, okay, so somebody said no. I realize it's kind of like scary to speak up in a recording, so the correct answer is actually no. Here's the reasoning. Oftentimes, this will produce the best case behavior, but we cannot guarantee that it will. Okay? So suppose that we have the array list like so. Right? Do you guys see if every value in our array list is n, right? If I remove n, what's going to happen is that the sum modulo n stays the same, right? If I don't change the value at the first index, that's what this implementation is considering. It's saying, what if we just put first back in? What could potentially happen is if our array was like so, even though our sum decreases by n each time, we're still always going to be going to the same bucket as before, right? Because our sum mod n stays the same. You guys see that? So what we want to ensure is that our sum mod n must change each time. Actually, let's do an even stronger claim here. I want us to somehow evenly distribute the lists so that every bucket has a list, okay? In order for every bucket to have a list, one idea is what if the sum decreases by 1 each time, okay? So let's say the sum starts off at n. Then the next time around, we want the sum to be n minus 1, because then we're going to the bucket right below it. Then the next time around, we want the sum to go to sum minus 2, and so on. So if from the previous part, we've concluded that doing first plus last keeps the sum the same, in order to decrease the sum by 1, all we have to do is say minus 1 here. And what we've ensured is that in the previous iteration, if we went to this bucket, let's say we go to bucket 1, then the next time around, we're going to go to 1 less than that bucket. We'll go to bucket 0, right? And then the next time around, we'll go here, right? And so on, until we've equally distributed the list amongst the array. Yeah. And then the array is all zeros is another good instance. Instead of having all n's here, somebody voiced in the chat, very smart, is we can also have all zeros, right? This is another, actually, this is a better possibility than what I described. I like it better. So this is a better case. But yeah, any questions about any of this problem?